In this video here, we're going to take a look at Simpson's rule. Now, Simpson's rule is a numerical method that is used to approximate the value of a definite integral. And it works in a similar way to another numerical method that you should already be familiar with, which is the trapezium rule. So Simpson's rule works by splitting the area under a curve into an even number of strips of equal width and then approximating each section of the curve by using a quadratic function. Now, what I've also included here is this diagram, and I'm hoping that this diagram here will help illustrate the concept of Simpson's rule and why we can use Simpson's rule to approximate the value of a definite integral. So to begin with here then, as we can see, right, we have this curve here. Okay, so I'm going to label this curve then as y equals f of x here. Like so. Now, again, as we can see here on the diagram, right, we also want to find the area underneath this curve then between a and b. And we know then by basic integration here that this will be a definite integral. So this here then is a definite integral of f of x with respect to x here from a to b. Okay, so the first thing that we require here, as we can see here, is an even number of strips. This is really, really important, right? So let me just highlight this here. We require an even number of strips of equal width. Now, this condition here is really, really important for Simpson's rule. In fact, Simpson's rule doesn't work with an odd number of strips. And the reason for that then is because what we actually do here is we pair the strips together. So clearly, if we have an odd number of strips, we'll always get left with one strip on its own, right? Which we clearly can't pair up. So we do always require an even number of strips. So in this case here, as we can see, right, we have strip 1 and strip 2 here. And then for strips 3 and 4, let me just do these in a different color. So strip 3 and strip 4 here. Now I've labeled strip 1 and strip 2 in a different color to strips 3 and 4 for a reason. Because what I'm going to do now is pair strip 1 and strip 2 together. So once I do that here, I get my first section underneath this curve here, right? And as we've mentioned here then, what we do is we approximate the first section here then using a quadratic function. That corresponds then to this red curve here. So this red curve here then corresponds to the quadratic function for my first section, okay? We also do the same here then for the final two sections, well, sorry, not sections, but strips here. So strip 3 and strip 4, we pair those together and I get another section here underneath the curve, right? And as you can see then, that corresponds to this blue curve here, okay? And the magic of Simpson's rule here is that underneath this first quadratic function here, we would integrate that. We would find the area then just by using integration. We'd have the first part of this area here, so it would be this area here up to this point. We'd then do the same with the second quadratic function here. Again, we'd integrate this, find the area then, and that would be my second area. And then finally, if we want the approximation then for this integral here, we just add those two areas together, and there we have it. That would be our approximation here. Okay, so Simpson's rule is very, very handy for integrals where the process of integration isn't straightforward, or we might not even be aware of how to actually integrate that given function. Okay, so in that case there, we just approximate it by using Simpson's rule. Okay, so as I've mentioned here, very, very similar to the trapezium rule. And in fact, Simpson's rule, generally speaking, is going to be more accurate than the trapezium rule. And the reason for that is because rather than using straight lines as we do for the trapeziums, as we go here, what I'm actually doing here is using a quadratic function. And as you can see, then it's pretty close to the original curve here, right? Using this red curve here. And same again for this blue curve here. Again, it's pretty close to the original function, right? So generally speaking, Simpson's rule would be more accurate than the trapezium rule. So I do appreciate that I haven't actually given Simpson's rule here yet, or the result for Simpson's rule. So we're going to take a look at that now on the next page. So that concludes everything for this page. Let's have a look now at Simpson's rule more formally. So let's just take a more formal look here then at Simpson's rule. Now, Simpson's rule is a straightforward result, but unfortunately is not given in the formula book. And as such, then you will have to memorize it. Now, I personally find this quite stupid, given that the trapezium rule is given in the formula book. Simpson's rule isn't for some reason. I don't know why that is the case, but unfortunately, just one of those things, right? So we will have to just memorize Simpson's rule. So for Simpson's rule then, for two n strips of width h, this is given by the following result here. So as we can see then, right, and at first glance, this might look a little bit messy here, but truthfully, it's not too bad. So what I've got here then is the integral of f of x with respect to x here from a to b, just as we saw on the previous page then. And then for Simpson's rule here, this is given by the following. So this will be approximately then 1 over 3 times by h. So don't forget then, h is just my width here of each strip. We then times this by the following. So we have y0 plus y subscript 2n here. So this y0 and y subscript 2n, these are my endpoints. This is my first value here, and then y subscript 2n is my very last value. And we also have 4 times by y1 plus y3 plus, so the next one would be y5 plus so on and so on, all the way up to y subscript 2n minus 1. So hopefully what you recognize here then, these are my odd values, right? So I sum all of the odd values up, we times that by 4, and we do the same here then for the even values, but we just times it by 2. So we have 2 lots of y2 plus y4 plus so on and so on, all the way up to y subscript 2n minus 2. So this bracket here then is the sum of the even values. And again, we times that by 2. Add everything together here inside this bracket. Don't forget to times it by 1 over 3 times by h here. And what that gives me then is an approximation to this integral here, okay? Or I should say this definite integral, right? And obviously the whole point of Simpson's rule is we like to use it for integrals that we can't really evaluate using our standard methods here, right? Where maybe we can't use integration by parts, we can't use substitution, we might not be able to use trigonometric identities, so on and so on. In that case, that's where we want to use numerical methods, right? That's the whole point of numerical methods. It allows us to calculate, for example, definite integrals where our standard methods and our standard rules don't really apply, okay? Now, as I mentioned, right, this looks a little bit complicated at first glance, but there's an easier way to think of this, okay? So you might find it more useful to think of this as the following. So the integral then of f of x with respect to x here from a to b is approximately 1 over 3 times by h times by the endpoints, that's y0 and y subscript 2n here, plus 4 lots of the odd values, plus 2 lot of the even values, okay? So that's personally what I try and remember here. Like I said, this isn't given in the formula book, so unfortunately you do have to memorize it. And this is the way that I would try and memorize Simpson's rule here, okay? So there we have it in terms of an introduction here to Simpson's rule. We don't need too much more. So that concludes our introduction here to Simpson's rule. Let's just have a look now at an example for Simpson's rule. So let's just get started then with this one practice question here for Simpson's rule. So straight away, what we can see here then is we're given this function f. So f of x equal to the square root of 4 plus x cubed here. For the first part of this question, then part A, it just says use Simpson's rule with 4 intervals to find an approximation for the integral of f of x with respect to x from 0 to 2. So to get us started here then for part A, because we're not given the result then for Simpson's rule in the formula book, let's just start by stating Simpson's rule here, or the result for Simpson's rule, I should say. So in that case then, the integral here, so the integral of f of x with respect to x from a to b will be approximately, so it's 1 over 3 times by h, and then we times this by here. We have the endpoints, that would be y0 and y subscript 2n. So endpoints. So we have the endpoints plus, we have 4 lots of the odd values, or the sum of the odd values. So 4 lots of the odds here. And then we have 2 lots of the evens here. Like so there. And there we have it. So this result here then is Simpson's rule. And I do think it's important for a Simpson's rule question just to start by actually stating the result then for Simpson's rule. As I mentioned, right, we're not given this in the formula book. And that's the way that I'd recommend trying to memorize Simpson's rule here. Now, the first thing that we need here then for Simpson's rule is a table, just like we do for the trapezium rule. And what I also need here then is h being my width here. So for h then, Nice and straightforward to evaluate here. So we do 2 minus 0, so it's the upper limit minus the lower limit. So 2 minus 0, and that's all over then the number of strips or intervals required. So given that we're using 4 intervals here, we divide by 4. I get 2 minus 0, which is 2, all over 4, which gives us 1 over 2 there. Okay. So now that we have the value of h here, let's just set up our table of values here. So in the first column here, we have xi and yi, or x subscript I and y subscript I here. And then for the values of x here, well, this corresponds to the widths, right? So we start with 0, and then we just add a half as we go. So 0 plus a half gives me 0.5. You then get 1, 1.5, and then clearly 2 here. Okay. And now for the corresponding y values, what we need to do here is use this function and just substitute the values of x in as we go here. So clearly when x equals 0, we get the square root of 4 plus 0 cubed, which just gives us the square root of 4, which clearly just gives us 2 here. Okay, so let's just keep going then when x equals 0.5. Now clearly, for the next set of values here for x, right, so x equals 0.5, 1, 1.5, and 2, we will need to use our calculator, right? These values will not be integer values. So in that case then, just use your calculator here. I get 2.031, so on and so on. Do try and keep as much degree of accuracy here as you can as you go, just so that we can ensure our final answer is accurate here, right? We haven't lost any degrees of accuracy in terms of rounding, within the question. When x equals 1 here, we get 2.236, so on and so on. So when x equals 1.5, we get 2.7157, so on and so on. And then finally, when x equals 2 here, we get 3.4641, so on and so on. Okay? So in that case then, we've now got everything that we need here to find an approximation for this integral here. So in that case then, the integral of f of x with respect to x from 0 to 2. So f of x here, right, is the square root. So it's the square root of 4 plus x cubed with respect to x here from 0 to 2. This will be approximately then following here. So we get 1 over 3 times by h. So 1 over 3 times by h, which is a half. So 1 over 3 times by 1 over 2. And then we get the following here. So let me just use square brackets for this bit here. So to begin with then, we have the endpoints here. So my endpoints then are 2 and 3.4641, so on and so on. So 2 plus 3.4641, so on and so on. Like so. So that's the endpoints dealt with there. We then have 4 lots of the odds here. Now, just in case you're confused what actually corresponds to the odds and evens here, right? We start with this being y0. This is y1. This is y2. This is y3. And then finally, this is y4 here. Now, clearly then, y0 and y4 are my endpoints. In that case then, y1 and y3 are my odds. And in that case, we just get left with one singular even value here, which is y subscript 2. Okay. I get 4 lots then. So plus 4 times by the odds here. So we have 2.031, so on and so on. 031, so on and so on. Plus 2.7157, so on and so on. So that's 4 lots of the odds there. And now we do 2 lots of the evens here, which is just 2 lots of 2.236, so on and so on. Like so here. Close the square bracket here. So all you need to do now is just use your calculator here, right? Evaluate everything inside the square bracket here. We then times that by 1 over 6 here, right? Because 1 over 3 times 1 over 2 is just clearly 1 over 6, right? Times those together. And what this will give me here then is an approximation for this integral here. So in that case then, what we get here is approximately, and I'm going to round this to 3 significant figures here. I get 4.82 here, and hopefully you get the exact same to 3 significant figures. Okay, so 2, 3, significant figures here, like so. Okay, and there we have it. So that gives us the solution here to this one practice question for Simpson's rule. And that actually brings us to the end then of this video here on Simpson's rule.